This is the first video in the 5th unit. This is on exponential functions. As you can see on the screen, we have a general form of an exponential function. We have f of x, it is a function, is equal to ab to the x. The x, of course, is the exponent. The b is the base of the exponential. And the a is the initial value. Later on, when we do some applications with exponential functions, the initial value will be the amount of money you start with, or the bacteria that grows in an exponential way, either increasing or decreasing. We can have growth or we can have decay. There are two types, basically, of exponential functions. You have exponential growth and exponential decay. And the decay, I don't like the way that y turned out, the decay function, they all have to do with your base. So if it's a growth function, the base is going to be greater than 1. If it's a decay function, then the base is going to be between 0 and 1. The base can never equal 1. It's not an exponential function if the base is 1. So if, for instance, you had 2 to the x, that would be a growth. If you had 1/2 to the x, that would be decay. Or you could have a function that was 2 to the negative x. And that, of course, these are the same thing, right? Negative means the 2 needs to go into the denominator. The basic graph of an exponential function is going to be shown here. So we see we're going to graph y equals, or f of x is equal to 2 to the x power. So this particular one, if I'm using the same general formula that I did before, ab to the x power, you'll know that the exponent is still x, b, the base is 2, and the initial value is 1. And because it's 1, it is just left off. So what we want to do is we want to graph this, and so I have my xy axis, and I've used my points that I normally use right around, because I want to see what happens right here around the y-axis. So I've chosen x values that are on either side. So I have here's 1, 2, 0, -1, -2. All right. So when I put in, I'm going to start with 0. When I put 2 to the 0 power, anything to the 0 power is just 1. 2 to the first, 2 to the second power is 4. And then with the negative exponent, if I have 2 to the -1 power, that would be 1/2. And 2 to the -2 power would be 1/4. So if I graph these points, at -2, I have a point that's just barely, that'll be hard to do. I'm going to go ahead and do 1, 2, 3, 4. And if I have -1, that's at about 1/2. 0 is 1, 1 is 2, and 2 is 4. This is an exponential growth graph. The graph has an asymptote along the x-axis, which is the point y equals 0. And really, to graph an exponential function, you need two basic points. You need this one at 0, 1. So if I'm drawing this out, it would be 2 to the 0 and 2 to the first, whatever your base is. So you go over 1 up 2. You know that the asymptote is at y equals 0 unless it is translated up or down. So you could do a function of any. You could do 6 to the x. This would be still 1 and 6. So to graph that easily, you go over 0 up 1 and over 1 up 6 and draw it in. So exponentials are fairly simple to graph. This is a reminder that an exponential function can also be graphed using transformations. I have here written a plus or minus a. Remember that a here is the initial value. and that is a reflection over the x-axis. So if that's positive, it's not a reflection, it'll look like growth or decay. And then if it is negative, it will be a reflection over the x-axis. The b is the base. This is the base. And then with the exponent, I have a plus or minus c. Plus is left, minus is right. And then out to the side, and sometimes they do it a little differently. They'll put the d, they'll say d plus or minus ab to the x. They'll put the d out in front, but either way, that is a transformation up or down. Please have these in your notes. We've done transformations over and over and over again. They work the same way with exponentials. So on this graph, you can see that I have the graph of 3 to the x. The parent function is 3 to the x. It's really small, 3 to the x. Okay, and then it is moved to the left 1 and down 3. And so that's how I can graph it. So the procedure here is to graph 3 to the x. And remember, I need 2 points. I'm going to go ahead and write here. I need 0 and 1. Anything to the 0 power is 1, and 3 to the first is 3. So I'm going to go over here, up 0, 1, and then 1, 3. And so I have a graph. This is what the graph looks like. Blue is 3 to the x. All right. Now what I need to do is I need to move this left 1. So I take these 2 points and I move to the left 1 and down 3. So there's my point. And then this point, left 1, down 3. And the asymptote, which was at y equals 0, is now going down 3. So 1, 2, 3. So here's my asymptote. And my actual graph follows that. And that is my transformed. So I really only need 2 points. And you can graph any base knowing 0, 1, and then apply the transformations to that after. E is actually a number. It's a constant value. It's irrational, however, because it is a never-ending decimal. You can see there on the screen that E is about 2.7182818281828. So unlike pi, it does repeat a pattern, but it's determined using calculus. This letter E, remember that pi is found by taking the pi is equal to the circumference of a circle divided by its diameter. E is not that simple. E is, in calculus, it is taking the limit as n approaches infinity of 1 plus 1 over n to the n power. So if you, as n goes to, both n's go to infinity, you approximate this value, 2.718281828. So to sketch the graph of f of x equals e to the x, you would actually be doing the graph of 2.71828 to the x power. So it's going to look very similar to 2 to the x. So if I use the same 2 points, if I use 0 and 1, anything to the 0 power is 1, and e to the first would be just e. And that is approximately 2.7. So if I'm graphing this, right, I have 0, 1. I'm going to have the same asymptote at y equals 0, and then at 1, I'm going to do 2.7, which is about here, and here is my graph. So this is a growth function. If I were to graph the graph f of x is equal to e to the negative x, remember that a negative exponent just means 1 over e to the x, this would be a decay function. This would be a decay function. So if I change points, it will still go through here, because if x is 0, e is going to be 1. And then, but this time, negative 1 is going to get me my 2.7. which is about here. And so instead of it being a growth function, this is going to be a decay. The domain and range are the same. The asymptote is the same. The only difference is that the function goes through, and I didn't get it quite, it's hard to go backwards. It is going to be the graph that is a decay function instead of a growth. One very important application of exponential functions is compound interest. And the compound interest formulas that I'm showing here and these are very simple. The ones that actuaries actually use to do financial calculations are much more complicated. And we'll be working with some of those towards the end of this unit when we do applications. But here are some very simple ones. You'll see here that A is the amount. Right here, A is the amount after. Remember from this part right here is the rate. 1 plus R over N. R is the rate that's given, usually in percent, so you want to change it to a decimal. N is a compounding period. That would be N is the compounding period. This is the same N, compounding period, and T is in time. Usually in years, but it can be any time if it's exponential. P is the initial amount. So yearly, that N would be once, quarterly would be 4 times a year, monthly is 12, and daily is 365. So those are, now that would be if you have different compounding periods, that you get interest that is compounded once a year, 4 times a year, 12 times a year, 365 times a year. You go from 365 to something that is compounded continuously, then the constant, or the base here, the rate is going to be E. And remember that E is a constant value. We just saw it on the previous 2.71828, ... Okay. R is still the rate in decimal. T is time. This is the amount after. And this is the initial amount. Principal is what they call it. Principal. This is number 53. You're going to actually be working this one in class. I'd like for you to copy the problem down. I've given you the 2 formulas for compounding periods. You'll notice that there's a table here set up that these are the compounding periods in along here, and then these are the amounts. The A corresponds to, of course, the A in the 2 formulas. It says, I want you to substitute the known values in your equation and store in y equals in your calculator. So the A part, right, the A equals, you're going to put the known values in here. And I've already copied the known values here. The initial amount was $2,500. The interest rate was 2.5%. The compound, I'm going to leave N. N will be X. Make sure that you're not in polar coordinates if you haven't changed your calculator before. And then the time is going to be 10 years. So the only thing that you're changing in this formula to get the amount are the number of compounding periods per year. So this would be 1 compounding twice semi-annually, quarterly, monthly, daily, and then continuously, and you're going to use E. And so I want you to reset the window so that you can see the graph, and then set in the table set area, its second table set, you're going to change the independent to the word ask instead of auto, and then you're going to record the values in the table above. So it's going to ask you to enter the value for N. So the first time you do it, you'll put 1. It'll come out with an answer, then you'll put 2, then 4, then 10, 12, then 365, and then you will, instead of using this formula, you will then switch for continuously to APERT. And then you only need to do it 1 time, so that you're going to put in your rate here. Your time is 10, so it will be 2,500 ERT. You know what the P, the R, and the T are. E is a constant. So just do that one in your calculator. So I'd like for you to work this problem before you come back to class, and we will talk about this. We're going to be doing a lot of application, and so I want you to be very familiar with your calculator and how it works. And I would like for you to be able to set up these problems and know these formulas by memory. See you in class.